All right, folks, good morning. Let's go ahead and get started. So last time we started talking about a technique. Anybody remember what the name of that technique was? It was infrared spectroscopy or IR spectroscopy, right? And we talked about the fact that you get these spectra, and what's on the y-axis? Well, almost, but not for the y-axis. Went from 100 to essentially 0. But we don't call it absorption because it goes from 100 to 0. We call it the opposite of that, which is percent transmittance, right? So it's kind of the opposite of absorption. And then what was on the x-axis? Wave number. Wave number was on the x-axis. Where do we start? 1500. That's right. We're going to start at 1500. We're going to start at 1500 wave number, and we're going to draw a line. And everything to the right of 1500 is called what? That's right. That's the fingerprint region. That's right. And it's got a lot of useful information, but it doesn't tell us a whole lot because all organic molecules have a lot of stuff over there. So it gets clumped up and jumbled up. And so now what do we do? How far of a step do we take? Yeah, we take a 500 foot. We take a 500 wave number step and we go to 2000. We draw another line. What's between 1500 and 2000? What region? This sp2 region, right? So this is where you're going to find things like carbonyls. So that can be ketones, esters, aldehydes. You're going to find things like carbon-carbon double bonds. You're going to find things like carbon-nitrogen double bonds. Anything that's sp2 hybridized, you're going to find in this region. Okay? So if you don't see anything there, you know you can't have anything that's sp2 hybridized, right? Well, now we're going to take another 500 wave number step, and that's going to get us to 2500. And I'm running out of space. These might not be quite to scale. And what do we call this region?
SP region.
Yeah, this is the SP region, right? So we've got SP. And what are we going to find here? We're going to find things like carbon-carbon triple bonds, carbon-nitrogen triple bonds. Anything that's sp hybridized, we're going to find there. Okay, those are just some examples. Okay, and you'll see absorptions there. 2500 to 4000, what do we call that? It's the hydrogen region. Right, so this is the H region. Right, and you're going to find CHs, right? And so you'll find CHs kind of over in here. And then if it's sp3 hybridized, if it's attached to an sp2 hybridized carbon, it'll be moved over just a little bit. If it's attached to an sp hybridized carbon, it'll appear even a little further over. We talked a little bit about that. And we also talked about being able to see things that look about like that at around 3300. What were those representative? Alcohols, that's right. Right, and so we can find alcohols quite quickly. We also talked a little bit about a messy broad one that'll go kind of throughout the whole thing, and that we'll also see a peak over here in the sp2 region. What would that be? That would be a carboxylic acid. So remember, carboxylic acid has an OH, but it also has a carbonyl. So you're going to see both of these. And this gets very broad, overlaps a lot of the other stuff. And we worked some examples from the old ACS study guide to determine that. So essentially, what can we get out of IR spectra? That's right. It's going to tell us what kind of functional groups we have. It's going to tell us much about how they're connected together. In other words, could you tell if it's 2-butanol versus 1-butanol? Not easily. And in this class, not at all. You know you have an alcohol. So how in the world would we distinguish between that alcohol and that alcohol? It turns out we need another type of spectroscopy. That's what we're going to talk about today. We're going to talk about nuclear magnetic resonance spectroscopy, NMR. Okay? If a chemist, and to some degree I would probably say even a polymer scientist, if they had a choice of only one instrument to have, it would be an NMR spectrometer. Okay? There are entire sequences of graduate courses on NMR spectroscopy. We are just going to cover the very thin layer of it. Okay? That's all you really need to know for this class. When I teach it in Chemistry 255, I actually only teach one additional lecture. So you're essentially getting half of what I cover to the undergraduates that are taking the what I call the organic sequence for the chemistry majors. Okay? And then we have an upper level course on spectroscopy at the undergraduate level, and then we have a graduate course on this. But this is really the coolest thing because it allows us to know what functional groups we have from IR, and NMR then allows us to connect them together in a way that we can actually build the structure. When you all heard me talking about the magic microscope sometimes, this is what I was talking about. Okay? So this technique is a very valuable technique, and it can do a heck of a lot more than we'll ever be able to talk about today. So you all are already familiar with nuclear magnetic resonance. You have either you yourself or you probably may know a loved one or a friend who's had to have an MRI. MRI is magnetic resonance imaging. It is nothing more than the medical version of NMR. Okay? That's what an MRI machine looks like. People won Nobel Prizes for this in 2003. Why is MRI such an important technique? Yeah, you can look inside the body without having to get a knife. I don't have to cut you open. I don't have to bombard you with x-rays. All right, I can see what's going on inside a human body and image it. Now, the nice thing in medicine is they take the NMR data and they're able to overlay that in a way that they get a nice image. Chemists do not get these nice images. We do not get an actual picture of a molecule that comes out of these things. We have to deduce what that structure is. Okay? And we're going to talk a little bit about that. So, how many people in here were familiar with MRI coming in? Yeah, you've heard the term before. Okay? So if you ever go and get an MRI, the thing you should be thinking about is they're getting ready to do an NMR experiment on you. And that's what they do. Okay? They put you in this big magnetic field, and they basically flip your protons, and you'll understand what that means here in just a moment. This is what an NMR looks like for a simple organic molecule. That looks nothing like that, but it's the same technique. Okay? What do you see when you look at this so-called spectrum? You see this x-axis that's called chemical shift. The y-axis, which isn't drawn here, is intensity. Okay, so you can tell that that peak here at a little past 3 is not as tall as the peak over here that's just past 1. Okay, so chemical shift tells us something about the molecule. The intensity tells us something about the molecule. And the shape of the line tells us something about the molecule. We call these singlets. They're just a single peak. That's why they're called singlets. Okay? This little peak that you see at 0, it is not part of the organic molecule. This peak that is at 0 is called tetramethylsilane. It is an internal standard, and it's used to define 0. We arbitrarily assign it a value of 0, and everything else is relative to it. Okay? So I would say that this molecule, which is MTBE, methyl tert butyl ether, It has a singlet at about, oh, I don't know, what is that, 1.2, 1.3, and it has another singlet at about 3.2 or something like that, okay? This signal comes from these hydrogens on this methyl group. This signal comes from these hydrogens that are on those 3 methyl groups. When I look at that, I see MTBE, but I've been doing NMR since I was 18 years old, okay? So, it takes a lot of practice to be able to look at a spectrum in your mind, be able to visualize what that molecule really looks like, okay? MTBE used to be added to gasoline. It was an oxygenating agent added to gasoline. It is no longer added to gasoline because it leaks and gets into the water and it's carcinogenic. But you can actually detect it in water using this technique called NMR, okay? And this NMR is actually looking at the hydrogens. This is called proton NMR, okay? So we're only looking at the hydrogens. These peaks come from these hydrogens, not the carbon atoms, not the oxygen atom, okay? It is from the hydrogens. So we're looking at the hydrogens in the molecule. Now let's think back to MRI. What do you think MRI is looking at in the human body? What do you have? What are you mostly made of? Water. What does water have? It has oxygen and what? And hydrogen. It's looking at your hydrogens. When they do an MRI experiment on you, they're looking at your water hydrogens in your tissues. And if, for whatever reason, I'm not exactly sure, you'd have to ask a physicist, but water in one particular type of tissue will appear at a different chemical shift than water in a different tissue. And they take that information and magically somehow are able to generate an image out of it, which is kind of nice, okay? So they're doing experiments on your water molecules. This is another simple organic molecule. How would you name this molecule? CH3, CH2Br, how would you name that? What's the parent? Pardon? Ethane? Yeah. What's the substituent? Bromo. So we would name this bromoethane. That's right. This is just simple bromoethane. Could also be named ethyl bromide, but we'll go with the regular name. Okay. So this is bromoethane. For some reason on this figure they say 1 bromoethane, but there's no such thing as 2 bromoethane. I don't know why they put the number in there. What's different between this spectrum and that spectrum?
Color.
Color, all right, that's true. What happened to the 60 and the 20? Yeah, it's not there anymore. What else is different? X and Y are the same, I mean in terms of the numbers, but certainly these peaks are at different positions. Yeah, I'll agree with that. That's hard to tell. Maybe they are. You mean here? Maybe.
It shows you the range on the x-axis.
Okay. What else? What was the shape of these? Straight, single lines, right? Singlets. What about the shapes of these? And these are blow-ups of these peaks. So this, whatever Pepto-Bismol colored one, right? This is that one, just so you can see the shapes better. What can you tell me about the shapes? There's several peaks. Yeah, we call these multiplets. Okay, we call this one a triplet. Can you tell me why we call it a triplet? There's 3 peaks. What do you think we call this one? A quartet. Yeah, it's a quartet. It's 4 peaks. Yeah. So something's going on here, right? This clearly doesn't look like that. It looks different. And those different multiplets and those different shifts and where they're at tell me that I've got bromoethane. Okay, we're going to figure out why these are actually shaped the way that they are. But when I look at this spectrum, I know that this has to be bromoethane. Okay? by how all of these things are shaped. And you're going to learn a little bit about this today. You're not going to learn a ton about it, okay? You will know enough to be dangerous. You will know enough that if you ever decide to take 255, you'll have a leg up. Or chemistry 255, you'll have a leg up. But we're not going to be able to solve big organic molecule structures from our work today. All right, so why does NMR work? Right now we're going to be talking about proton NMR, so we're only looking at hydrogen atoms. And it turns out that we call it proton NMR because a hydrogen atom only has one proton and it's got one electron. And the electron's in a bond with something, right? So it's really a proton. Okay? It's just a single particle. But it turns out, for whatever reason, this comes out of quantum mechanics, and we're not going to get into that. I'm not a physicist. But it turns out that in protons, or in hydrogen atoms, the proton spins like a top. What's the charge on a proton? It's positively charged, and it's spinning. And when you were in grade school, you might have done an experiment with your teacher where you built an electromagnet. Took a nail and wrapped some wire around it, hooked it to a battery, and then picked up paper clips with it or something. The charges that were moving through the wire created a magnetic field. It doesn't matter whether the charge is positive or negative, it's just a charge that's moving. And all charges that move create a magnetic field. So if I take a positively charged thing and I spin it, it becomes a magnet. All of the hydrogen atoms in your body are magnets. Okay? They are magnets. They have a north pole and a south pole. Okay? You've got little tiny magnets all over in your body right now. Okay? What happens when you take two magnets and put them near one another? They can repel or they can attract, right? So what do you think happens when they put your body in the big magnetic field in the hospital, in the MRI machine?
Attracts?
It either attracts or it repels. Yeah, that's all it can do. It can either be aligned with the magnetic field or against the magnetic field. That's all it can do. Okay? They're not randomly oriented anymore. And we can use that information to develop an image. Okay? It's kind of amazing that we can do that if you ask me. It almost kind of sounds like alien technology, kind of, right? It's hard to imagine. Now, if you're outside of a strong magnetic field, it turns out that your magnetic moment, if you will, this arrow, so think of it as like going from south to north, okay? That's all it is. It's pointing in one direction because it's spinning like this, creates a magnetic moment that goes this way. When you're outside in something that doesn't have a whole lot of magnetic, of course the Earth has a magnetic field, but it's pretty weak, okay? Your protons can be oriented this way, 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 I mean, at random. But if I take those protons and I place them into a strong magnetic field, which is represented by B0 and this big arrow, so this is the MRI machine, there's only two things that your protons can do. They can either spin such that their magnetic moment is aligned with the magnetic field, or such that it is opposite. That's the only thing that they can do. Okay? They can't be oriented to the side. They can either be up or down. Spin up, spin down. Okay? Are those spins that are up equal to the spins that are down? If you look at what I've got on the board, if you count them, is the number of arrows pointing up equal to the number of arrows pointing down?
4 and 3.
Yep, so is that equal? It is not. Which one is more? Up. What is B0? Up. Most of your protons will align with the magnetic field, but some will not. This comes out of quantum physics. It can only be in two states, spin up or spin down. Okay? And we can use this to determine. Okay? All you have to do to go from a spin up to a spin down is put energy in. It's called spin flipping the proton. Okay? So I've got my proton in my external magnetic field, this is where it's aligning, and all I gotta do now is put energy into it, and I can spin it the other way, okay? So there are only two nuclear spin states. I can measure this amount of energy that it takes for this proton to absorb to do that. I can measure that energy using what's called an NMR spectrometer. Just like the absorption in IR, the absorption in NMR happens at different chemical shifts depending on what that hydrogen is attached to. Nature works very well, right? So if that hydrogen is attached to a methyl group, it will appear differently than if it's attached to an oxygen. It will appear in a different place, okay? And I can tell that quite easily, in part because of my experience, but because this experiment is so easy to do. It doesn't take much time to actually run an NMR experiment, okay? So what is this NMR? Well, we could go upstairs. I could show you what the NMR looks like. Some of you may have seen one before. All it looks like is R2D2 sitting there, and it doesn't look like it does anything, okay? It's a big can, all right? Just a big can. And this big can is actually a dewar that we put liquid helium in and put liquid nitrogen in. We use what are called superconducting magnets. We have to generate a huge magnetic field, okay? And in fact, the old NMR spectrometer we had, sometimes I would forget that my keys were in my pocket. And when I would go up near the NMR, it would literally tug on my pocket. You could feel it tugging the keys towards it, okay? It's that strong of a magnetic field, okay? And so, you know, people with pacemakers and other things couldn't go into the room with it because it would impact the pacemaker. The new NMR instruments actually have the magnetic field contained within the can, okay, through what's called shielding, but they're a little safer to be around, okay? So this magnet is cooled down to liquid helium temperatures, and it's a superconductor. It creates this huge magnetic field. And what we do is we put your sample in through here, down into the coil, what we call the coil, and it's now inside this big magnetic field. And so the protons either align with or against. And what we do is we have this computer system that sends a radio signal pulse to the sample and flips your protons from one state to the other. And we can measure through that coil, we can measure how much energy that took, okay? I am oversimplifying this. And in fact, people who are NMR spectroscopists would vomit at what I'm telling you all, right? I'm giving this to you as easily as I know how to, okay? And so what we get when you spin flip those protons, when you take the energy away, they fall back down to their original state. That's what we're measuring. And that gives what's called a FID. It's a little squiggly line that looks like this, okay? That's the data that you really get, okay? You measure the time that it takes for those protons to relax back to their natural state. And that looks nothing like an NMR spectrum. But we take that, we run it through a set of math equations, and thank goodness the computer does all this, and it converts that into the spectra that we see. So it takes this and converts it into peaks like we're used to see, okay, that we can interpret, okay? It's actually a fairly boring thing to go in and see an NMR, because again, it just sits there like R2D2's batteries are in dead, right? It looks like that. And about the only thing it does is hiss at you every now and then when you put in your sample. That's about all it does, okay? These are very expensive pieces of equipment. The NMR that we have upstairs was $400 grand 12 years ago. Some of them that are over in polymer science, I think we're close to $1 million. They're not cheap pieces of equipment to have, but they're very, very useful, okay? So that's what an NMR spectrometer kind of looks like. All right. I normally, as you all know, do not like to put a lot of words on my slides, but I'm putting words on my slides because you need to know these things that are in bullets, okay? You need to commit these to memory. You need to know that for proton NMR, the protons in different environments will absorb at slightly different frequencies. They'll appear at different places on the spectrum, okay? They'll appear at different chemical shifts, okay? And it turns out that the frequency, or the chemical shift, is determined by the environment that proton is in. If it's attached to an electronegative atom like oxygen, it will appear at a very different frequency than if it's on carbon. So electronegativity has a habit of making these protons appear in different places. Okay? The last thing you need to remember is that only nuclei that contain either an odd mass number and or an odd atomic number actually give rise to NMR signals. Not all elements on the periodic table, or all isotopes of all elements on the periodic table, will give rise to NMR spectra. But you know what? Fortunately for us chemists, the elements that you see there in the parentheses are pretty much so what we deal with every day. We deal with hydrogens. Hydrogen has a mass number of 1, or an atomic number of 1 and a mass number of 1. It gives NMR signals. Carbon-13, the isotope of carbon that's called carbon-13, has a mass number of 13. It gives NMR signals. Fluorine-19, phosphorus-31, those all give NMR signals. So you can do phosphorus NMR, you can do fluorine NMR, you can do carbon NMR, you can do proton NMR, you can do all kinds of different types of NMR. Okay? Very, very easy. All right? The first thing that you're going to need to be able to do when you look at an NMR spectrum, or a molecule, I should say, you're going to have to determine how many unique signals would I expect to see. Okay, you're going to have to look at a molecule and say, how many NMR signals would I expect to see? You have to determine the different environments of the protons. So for example, if we look at dimethyl ether, this very first molecule, I know that it's only going to give rise to one signal. Why? Why are the hydrogens on the left equal to the hydrogens on the right? They're connected to the same thing. And there's actually a mirror plane through there. And that mirror plane says that the left and the right are equal. Right? So if I was to take dimethyl ether and go get an NMR of it, I would see one peak and it would be a singlet. Chloroethane, I'm going to see 2 NMR signals. The CH3 is, these hydrogens are attached to a carbon that's only attached to another carbon. That's different than these hydrogens. These hydrogens are attached to a carbon that are attached to another carbon and a chlorine. These hydrogens are clearly different than these hydrogens because of what they're connected to. They're in a different environment. I know that if I look at ethyl methyl ether, I'm going to see 3 signals. Again, this CH3, these hydrogens are attached to a carbon atom that's only attached to an oxygen. This CH3, you might be asking, why isn't this CH3 the same signal as this? Well, this CH3 is not attached to an oxygen, it's attached to another carbon. Those are different. And then this CH2, of course, is attached to an oxygen and a carbon. So I'm going to see 3 different types of NMR signals for this molecule. Okay? You're going to have to practice that. Being able to look at a molecule and tell yourself how many unique signals you would expect to see. Because on the exam, you will be able to, in some cases, eliminate possibilities. If you look at it and go, well, that should have 4 signals and I'm only seeing 2, guess what? It can't be the answer. You can cross it out. Okay? Now, to get some of these, sometimes you're going to have to draw things out a little better, right? I mean, you could draw chlorocyclopropane like this, but it doesn't tell you about the hydrogens. You need to draw it like this. How many signals would you expect chlorocyclopropane to have? This is where model kit building can come in handy, for sure. I heard 2. What 2?
The hydrogen attached to the chlorine and the other 2.
Okay, so you're saying that this is different than these.
Yes.
Okay. I will agree that that is a true statement, but not complete yet. You got the 1 down just fine. This one is clearly different than these two because it's on the carbon with the chlorine. These are on carbons that are not attached to the, direct closest to the chlorine. But do you think that those hydrogens on the top of those other two carbons are the same as the hydrogens on the bottom two carbons? On the bottom two? Do you think that these hydrogens are the same as these hydrogens? If they were the same, would we expect to see a mirror plane through there? We would. Do we see that? We do not. There is no mirror plane that runs through this way. There's a mirror plane that runs through here. So this should be equivalent to this, and this should be equivalent to this, but this and this are not the same. Why is that? Because these hydrogens are on the same side of the molecule as the chlorine. These hydrogens are on the opposite side of the chlorine. They're kind of like cis and trans. They're very different. So actually we will see 3 signals for that particular molecule. What do you think for this alkene? How many signals would you expect to see? How many hydrogens do we have? We have 3. Are they all the same?
No.
This hydrogen's attached to a carbon that's attached to a... This hydrogen is attached to a carbon that is attached to, doubly bonded to a carbon. This hydrogen's attached to a carbon that's doubly bonded to a carbon. You might think that these two are the same, and this one is different, but these are actually different as well. Why are they different?
The plane of chlorine.
Yeah, so this one is closer to the chlorine than this one, isn't it? This one is cis to the chlorine, this one is trans to the chlorine. In fact, we will see 3 different signals for that molecule. Okay? We will see 3 different NMR signals for that molecule. Now imagine going from these small molecules to a huge molecule. Something that has, I don't know, let's pick on something that's not that big, 20 carbons and over 40 hydrogens. How many signals would you expect to see? A lot, right? And so these spectra can get quite complicated. The good news for you all is I'm not going to give you anything that big. And we're going to be dealing with some very small molecules in this class, okay? So, again, looking at the types of, or the number of signals. For 1,2-dichloroethane, both of those hydrogens are exactly the same. There's a mirror plane that runs through it. You'd only see one type of signal for all 4 of those hydrogens. Let's see, that is bromochloropropane, right? So 1,3. You will see 3 different signals. Chlorine is different than bromine. They're not the same. They're both halogens, but they're not the same. So you're going to see 3 unique signals, okay? This ester, I've got 2 methyl groups, but those methyl groups are going to be different. This methyl group is connected to the carbonyl. That methyl group is connected to an oxygen. Those are 2 different types of groups. They're going to give you 2 signals, okay? And then our good friend ethanol, 3 signals. One for the CH3, one for the CH2, and one for the hydrogen attached to the oxygen. Okay? We'll see 3 different signals. And in fact, people do use NMR to determine the purity of distilled spirits. Okay? You can take your moonshine. You won't have a $400,000 thing out in the woods, right? But you could take it upstairs and you can run an NMR spectrum and you could determine the purity of it by looking at the NMR. Okay? Happens all the time. People do that kind of thing. Not the illegal way, but okay. So, a couple of things that you need to keep in mind as you're looking at an NMR problem trying to solve it. Okay? The first thing you're going to want to do is count the number of signals that you have on the spectrum. Right? And if you say, oh, there's 5 signals, start eliminating molecule choices based on that. This one should only give 1 signal. That can't be it. That one only gives 2 signals. That can't be it. Well, these 2 give 5 signals. Well, okay, then it's going to be one of those 2. Now look deeper, right? So always count the number of signals first. Count the number of signals in the spectrum, look at your molecule choices, and try to eliminate based on that, okay? So when I look at that molecule, how many signals do I have? I've got 3 signals. This is a signal, it just happens to be into a triplet. This is a signal, it just happens to be a multiplet. And this is a signal, happens to be another triplet. We'll get into that splitting here in just a minute, as we call it, okay, the different shapes. This has 3 signals. Remember, this little signal that you see at 0 is that tetramethylsilane. You just ignore that. It's there for 0. Okay? The next thing you need to do is determine where your signals are on the chemical shift. And for proton NMR, your chemical shift is going to be approximately from 0 to about 12. It can actually go out further than that. But that's where most things come, is between kind of 0 and 12. Okay? So, if I have, so my NMR spectrum, I'm going to have chemical shift here, which is called delta. Okay, that's what chemical shift, the abbreviation of chemical shift. And I'm going to have intensity. And you can memorize all that. Right? There's only 1, 2, 3, 4, 5, kind of 6 places you got to kind of look at. Okay? Take a look at those different molecules that are up there, the different hybridizations of the carbons that those hydrogens are attached to. And then try to summarize for me a general rule. Where would you draw the line like we did in IR? Remember at IR we started at 1500? Where would you draw an initial line on an NMR spectrum and say, this is where I'm going to start? This is where I'm going to draw a line, and I'm going to look to the right and I'm going to look to the left of it, and it's going to tell me something. Given what you see there, about where would you draw that line? If you look at it in general, more or less what you see on the right-hand side, closer to 0, if you will, you see a lot of hydrogens that are on sp3 hybridized things. Of course, there's some sp as well, but you see a lot of sp3. Over here, what we call downfield, or deshielded, don't worry too much about that, we see a lot of what kinds of carbons? sp2. We see hydrogens that are either attached or close to sp2 hybridized carbons. Okay? Where would you draw the line between this sp3sp and the sp2? Pardon?
4.5.
Yeah, you're really close. I always come in and I draw the line at 5. So there's 0. There's 12. I kind of draw the line around 5. And I know that everything to the right of 5 is going to be hydrogens attached to sp3 hybridized carbons or sp hybridized carbons. What else can you tell me? I know that if that sp3 hybridized carbon is just attached to other carbons, it's going to be closer to 0 than if it has oxygens or halogens. They're going to appear a little closer to 5. So the more electronegative atoms that are attached to the carbon, it's going to pull it closer and closer to 5. The less electronegative atoms that the molecule has, it's going to push everything closer and closer to 0. Okay? And then from 5 to 12, I know I'm going to have, my alkenes are going to be between around 5 and 6. And my aromatic rings are going to be between 6.5 and 8. And I know that things like carboxylic acids and aldehydes are going to be out between 10 and 12. Automatically looking in those regions, I can eliminate a lot of choices. You know, if I see something out here at 12 that looks something like that at all, I'm gonna go, that's probably gonna be a carboxylic acid or an aldehyde. And I'm gonna look at all my choices and I'm gonna go, only one choice, that's probably the right answer, right? So you can do a lot of this by process of elimination. Okay. In your book, it's not tables 9.1, these are different slides. But in your book, you do have what are called chemical shift tables. They get into the details of where the chemical shifts will appear. You will not need those tables for my exam. You will need those tables for your homework. But my exams will not require you to go into real great depth to determine between the different choices, okay? So don't waste your time memorizing all of the different fine points of where things appear. Worry about this kind of thing. Okay, I know this is my SP2 region, this is my SP3 and my SP region. Notice that SP is going to be between 1.5 and 2.5. SP3 is going to be between 1 and 1.5. This is where you're going to see these types of things. Okay, and these are rough marks. Can I have something that's SP3 hybridized that appears past 5? You bet. Sure can. Okay, but it would have a lot of electronegative atoms attached to it. Okay. So these are good starting points for y'all to work from. Okay. The next thing you're going to do is you're going to determine what's called the integration of the signal. How many people know what the word integration means? What does it mean to integrate something? Anybody in here have calculus in high school? No? Integration means to find the area under the curve. That's all it means. You take all this math to figure out that all it means is measure how much area is underneath something, some sort of curve. Okay? That's what these little lines are, these little squigglies over the signals. Those are integral lines, and they tell us the area under those signals. And it turns out, in this case, if you took a ruler and measured from here to here, you would call that 1. And if you measured from there to there, you'd realize that it's the same as that, and that's also 1. And you'd realize when you measured that one, that it's about 50% more, so it's 1.5. That tells me the relative number of protons that are giving rise to that signal. The ratio is 1 to 1 to 1.5. What's weird about that ratio? What's weird about a ratio of 1 to 1 to 1.5? How many of you think I can give you half a proton? Can I give you half a hydrogen? I cannot. I cannot do that. That's called splitting an atom. And you can't split hydrogen because it's only got one proton. There's nothing to split. Okay? So, what are we going to do then? If I can't, my molecule can't have half a proton somewhere. What do I need to do?
It's a ratio. You just multiply.
I just multiply it out. What would you multiply by? 2. Yeah, so the ratio is really 2 to 2 to 3. Right? But the NMR doesn't know that. It just knows the relative ratio, which comes out to be 1 to 1 to 1.5. So we've got to figure that out. And does that make sense? Well, they gave me the formula here. C3H7Br, 2 plus 2 plus 3 is 7. So multiplying out by 2, as Rose suggested, gives me the actual number of hydrogens. Right? So if you know the integration, and you look at your choices and you go, well, that one's got way too many protons. That one's got way too many protons. This one's got the right number of protons. This one's got the right number of protons. You can eliminate half of them.
So is that value given, or is it calculated by hand?
It could be either. I could give you, I won't give you the lines and tell, here's a ruler, go measure. I won't do that, okay? But I would give you something like that that's above it. And you would have to know, oh wait, that's a half, I gotta multiply by something to get that to be a whole number. That would be fair. Or we could just give you the number. I could have just given it up there as 2 to 2 to 2 to 2 to 3, and you would have looked at the molecular formula in this case and known that that turns out to be the right number. Okay. The next thing you need to do is you've got to interpret the splitting pattern, and this is where things get a little complicated. And I know you're going, oh, now it's getting complicated? Okay, just relax, it's all right. It turns out that these splitting patterns tell us about the neighboring protons. What did I tell you that a proton was when it was spinning? It's like a top, and it's a little bitty tiny magnet. And we said that if we put a magnet in a magnetic field, it will either align with or against, right? But what happens when I put a magnet next to two magnets? It feels the effect of both magnets, right? So proton A, in this first example, it feels the effects of the instrument, but it also has one nearest neighbor, B, right? That is also a magnet. So HA will appear as a doublet. It feels the magnetic field of the magnet and its neighbor. It gives it that's what we call a doublet. So HB also only has one neighbor, so it appears as a doublet. So anything that's connected like this, we would have a doublet and a doublet. If I look at HA and HB here, how many neighbors does HA have now? How many HBs are there? 2. So HA appears as a triplet. It fills the 2 and the magnetic field. So it appears as a triplet. How many neighbors does HB have? HB, both of those hydrogens are equivalent, by the way, so they're only one signal. But how many neighbors do those hydrogens have? Those two hydrogens have HA as a neighbor, right? So that's how many? 1. And so it appears as a doublet. When I look at those peaks, I go, that triplet has to have 2 neighbors. I look at that doublet and I go, that signal has to have 1 neighbor. I'm starting to get pieces to a puzzle. How many people in here like to put jigsaw puzzles together? You're going to love spectroscopy. That's all spectroscopy is. You take the pieces that you get and you start putting them together until they make sense. Okay? I also know that a case like this, HA and HB, they're going to be triplets and triplets. Here's HA and HB where I've got HA has 3 neighbors, so it's going to appear as a quartet. HB has 2 neighbors, it's going to appear as a triplet.
So when counting neighbors, you would include hydrogens of the same type as well?
This leads us to a rule, and it is called the N+1 rule. That's not a minus sign. What does the N stand for? Anybody know? Anybody read ahead? Pardon?
Hydrogen?
It is hydrogen, but it's the number of what hydrogens? Of the neighbors. Always think of N as neighbors. And neighbors are just, for the purposes of this class, the neighbors are just the hydrogens that are on the next adjacent atom. Okay? Notice this. It makes sense. Hydrogen A has how many neighbors on the top one? How many HBs are there? 1. What's 1 plus 1? 2. That's why it's a doublet. HA here has 2 neighbors. 2 plus 1 is 3. So guess what? It appears as a triplet. All you got to be able to do is add the number of neighbors plus 1. It's the N+1 splitting rule. Okay? So you can start to see how things are put together. All right. So, you all now know that this molecule is C3H7Br. I want you to get in your groups and I want you to tell me what the structure is giving that spectrum. What is the structure of C3H7Br? take 5 minutes, get with your neighbors, work it out. You know you've got 3 carbon, 7 hydrogens, and a bromine. All you gotta do is put them together in a way that makes sense for that spectrum. Embrace the struggle. Just, there's the integrations. I forgot to pop that up. So it's 2 to 2 to 3. The integration. If you can't get the whole structure, it's fine. Put at least some of the pieces together. Couple more minutes. All right. Let's start by going through this a little bit. Looking at that, what's the first thing that we needed to do? We need to count the number of signals, right? We need to know that everything is to the right of 5, so I don't anticipate there to be any kind of sp2 hybridized carbon at all, right? There's not going to be carbon-carbon double bonds or any of that stuff going on, right? How many signals do we have? How many signals do I have up there? I've got 3 signals. That means I have 3 unique types of hydrogen. Also turns out I've only got 3 carbons, so guess what? Each carbon is going to have hydrogens on it that give rise to a unique signal. I know that, okay, by looking at that. What else do I know? I know that this signal is closer to 0 than this signal. What would make this signal be so close to 5? It's got to be something that's attached to that carbon that's more electronegative. What do I have in my formula that would be electronegative? The bromine, right? Yeah. So I've got, this has to be a carbon atom that has the bromine on it. Okay? And how many hydrogens are on this signal? What's the integration? 2, right? So I've got a carbon atom that's got a bromine attached to it and 2 hydrogens. I don't know what else is attached to it yet, but I know that that has to be that piece. It's the furthest down. It's got 2 hydrogens. That makes sense. Now let's look at the one way out here. I know it's going to be a carbon. It's, pretty close to 0, right? What's the integration? 3. That was the 3, right? And they're a little off, but that's 2 to 2 to 3, right? So this one integrates to 3. So it has to have how many hydrogens? 3 hydrogens attached to it. I don't know what else is attached to it yet, but I know that that has to be a methyl group, a CH3. Now that CH3, what's its shape? Is it a singlet, a doublet, a triplet? It's a triplet. So if n plus 1 equals 3, then what does n have to be? 2. So it has to have 2 nearest neighbors, right? So this CH3 has to be attached to a carbon with 2 other hydrogens on it. I don't know what else yet. Make sense? What's the shape of this signal at 3? At 3 point, what is that? 3.3, 3.4? What's its shape? It too is a triplet, right? So it has to be attached to a carbon with 2 hydrogens. Don't know what else yet. Okay. How many carbons did I just write up here?
Too many.
1 too many. Which means that one of these has to be the same thing. Which one is it? The CH2 in both of them, right? So this molecule is CHHBr, CH2, CH3. Those 2 hydrogens give that middle signal. And how many total neighbors does it have? 3, 4, 5. 5 plus 1 is 6. And if we look really careful and count, there's 1, 2, 3, 4, 5, 6. This is the spectrum for what? How would we name that molecule?
Propane?
Almost. Real close. 1 bromopropane, because we can have 2 bromopropane, right? So this would be 1 bromopropane, right? That's how it's all put together. And so you do this fragment kind of answers, right? You figure out what the pieces are. I just figured out what the pieces were to the jigsaw puzzle and I started putting them together. Once I put it together, now I ask myself, does it make sense? This is going to be the furthest down. That makes sense. It's going to integrate to 2 hydrogens. That makes sense. And it's got 2 neighbors. It'll appear as a triplet. Bingo. This carbon give rise to a signal. It's going to be a little further down than this one because it's closer to the bromine. It has 2 hydrogens, so it'll integrate to 2. That makes sense. And it's got 5 neighbors, so it should appear as 6 peaks, and it does. And then CH3, it's the furthest away from the bromine, so it's going to be closer to 1 or 0. It only has 2 neighbors, so it's going to appear as a triplet. Okay. Does that make sense? This takes a lot of practice. If your head's hurting a little bit right now, I expect it to. Okay? It's okay. It's all right. You're gonna figure this out. Okay? I promise. And so we put all the pieces together, and that's what we have, right? So now let's look at some spectra. Here's 3 molecules we're going to look at. How many signals would we expect for the top one? Well, I've labeled them for you, A and B, right? So we're expecting 2 signals, right? Now let's look at all of these spectra and see what they look like, okay? So if we look at, how would we name this? Two iodo propane. Yep, 2 iodo propane. There's 3 carbons, right? I expect to see 2 signals. I do see 2 signals. I see a signal here just around 1.8 or 1.9, and I see a signal over here about 4.4, 4.3, something like that. When we blow them up, we see that that's a doublet, and we see that that is a multiplet. It looks like 1, 2, 3, 4, 5, 6, 7 peaks. So is this A or B? Pardon? It is B, right? B has 6 neighbors. It should appear as 7 peaks, and it does. And it's attached to the carbon, directly attached to the iodine, so it should be the furthest downfield. A is a doublet because it has 1 neighbor. And this A and this A are identical because there's a mirror plane, right? So this has 1 neighbor. This has 1 neighbor, gives rise to the same signal. And we see that. Okay. How would we name this molecule? It is dichloroethane, but we got to do some numbers. Why do we have to do some numbers? Because I can have 1,2-dichloroethane, or I can have 1,1-dichloroethane. What's this one? 1,1. This is 1,1-dichloroethane, right? We're going to end up with 2 peaks again. Now notice, what's the hybridization on this? Is that sp3, sp2, or sp? Looking at the bonds. Are there any double bonds? Are there any triple bonds? So it must be sp3. Right? This is an sp3 hybridized carbon. But this hydrogen B, notice how far down it is. It's past 5. And I told you we draw a line at 5, but I said that's a rough line, right? Why is this one so much past 5? Because it's got an extra chlorine. It's got 2 chlorines instead of just 1, right? This only had an iodine, right? So it only pulled it down so far. This one has 2, so it gets a little further down, right? And so it's got 3 neighbors, so it'll appear as a quartet, and it does. This one has 3 neighbors, so it'll appear as, this one appears as the quartet, this one appears as the doublet, and that's what we see, okay? Same thing for the last one there. You all can go through that and figure that one out as well, okay? So go through and figure out what the peaks are, all right? So this is an example of what's called 1-nitropropane, right? And so this is the molecular formula. We can start to piece it together as well. So you can see that HB here, right, has 1, 2, 3, 4, 5, 6, and it's got 5 neighbors, so that's why it's there. This one, this triplet, this is C. It's pretty far down because it's attached to the nitro group, which is electronegative. And then, let's see, HA here is a triplet because it's got 2 neighbors. Okay? And again, we're always going to ignore this signal at 0. Okay. So why do we get these peak splittings? We've already kind of explained it a little bit. It's because the signal can sense the magnetic fields of its neighboring protons. And so if you had a hydrogen atom that had no neighbors, it would just appear as a singlet. We've already determined that. But if I stick it next to one other hydrogen, it will feel the effects of B0 and the effect of the neighbor. And so that's why it appears as this 1-to-1 peak height anyway, double it, or it's approximately 1-to-1, it's not always exactly 1-to-1. But the distance between these two peaks is also important. It's called a coupling constant, J. We're not going to get into coupling constants too much, but it's another piece of information that we chemists use to determine structure. But you won't need it for any of the exams any exam questions that I'm going to give you. And you literally just measure it with a ruler. Now you can do it with a computer, but you can measure that distance, and that's called a coupling constant. And tells us something about how the hydrogens are in 3 dimensions, which is kind of cool as well. Okay, let's skip that triplet. Okay, so let's look at some examples here. We'll work through a few things today. So let's look at this so-called problem 143. How many signals are we going to get for that molecule? Proton signals. Six? Where'd you come up with 6?
Well, there's 2 different kinds on each of those substituent groups.
Okay.
And then I figured there's the ones near the oxygen and the ones away from the oxygen.
Okay, so these and these, right? There's no hydrogens on these carbons, right?
Right.
So this, you're saying is different than this.
Mm-hmm.
You're saying that these are the same, but different than the others. You're saying that these are the same, and that this and this are different, right? So that's 1, 2, 3, 4, 5, 6. See if you're right. You are. Right? You need to draw out the hydrogens on these if you were having trouble with that. You can also build a model. You'll notice that there's a mirror plane that runs through here. That's why this hydrogen is the same as this hydrogen. Okay, that's why she was counting this as 1 signal. But this is different than this because there's not a mirror plane that runs through here. Oxygen is not a reflection of carbon, right? So, yeah, good deal. Try this one. Which structure shown below is consistent with this NMR spectrum? So we don't have a whole lot of time left. Take 3 minutes with your partners, work through this one. And it might be kind of difficult to see, I'll just tell you. This is a quartet, 4 peaks, this is a singlet, and that is a triplet.
That was from left to right? Quartet.
Yeah, from left to right. So this is a quartet, a singlet, and a triplet. Can we eliminate anything by counting the number of signals? How many signals do we have? We have 3 in the spectrum, right? 1, 2, 3. Does A, how many signals would A give me? 1, 2, 3. So it might be it, right? B would give me 1, 2, 3, and there's a mirror plane, so this would also be 1, 2, 3. So it'll only give me 3. D will give me 1, 2, 3. What about C? That's 1, 2, 3, 4. So it can't be C, can it? What's the right answer? You got a 1 and 3 shot, not a 1 and 4. I hear a vote for A. A makes some level of sense. What else do we have a vote for? Can't be C, we just eliminated C. The right answer is B. A made sense in the sense that you had a singlet, a quartet, and a triplet. The problem, and the same thing here, you have a singlet, a quartet, and a triplet. So how did I make that determination that it had to be B instead of A? Well, if you look at this, the quartet is the furthest down. The singlet is further up, right? This singlet is what would have been attached to the oxygen. So these would have been the opposite. The singlet would have been further down, and the quartet would have been further up. But here, I've got a quartet that's, these two hydrogens that's attached to this oxygen, they're going to be a quartet. They're going to be way far downfield. I've got this methyl group, which has two neighbors, so it's going to be a triplet. It's going to appear here. And then this has no neighbors, so it's going to appear as a singlet, but it's going to be a little further down because it's close to the oxygens. It's not directly connected to the oxygens, but it's close to them. So it's going to appear a little further down, but not further than this. Right? And so that's how I made that determination. All right, we will pick up next time with carbon NMR, which, trust me, is a lot easier than proton NMR. But we need a quiz for chapter 10. So I need you to turn in 10.40. Put your name on it. Turn it in on your way out up there on the table. And I will see you on Thursday. And we'll finish up NMR, and we will then jump into chapter 12. So please read ahead.